How do you get a collection of machines in a distributed system to agree on the same facts even when some of them crash? That problem is called consensus, and Raft is one of the best ways to solve it. In this video, we are going to walk through the core of how it works. Let's start with the easiest setup, because that is where the problem becomes more vivid to see. A client talks to a server and the server writes to disk. There is the whole system, one place for the request and one place for writing the data. It is simple and it is fast, but at the same time it is fragile, because there is only one machine, and if it dies, the data is also gone. So this is what we are trying to avoid. One failure takes the whole thing down. The usual answer is to replicate, and this is where we have a distributed system. You run several servers and they share the same state, so if one of them dies, the others still have the data. That helps with the crashes, but it immediately creates a new major problem. The copies can disagree. Here we have three replicas, and they are not telling the same story. Two of them is x equals 1, one of them says x is 2, and it is not obvious which value is the real one. That is the consensus problem. Can a group of machines decide on one result and actually mean the same thing by it? People usually break that down into three properties. First one is agreement. The healthy nodes eventually hold the same value. You do not want the cluster split into two camps that both think they are right. Validity. They did not invent the value, someone actually proposed it. And finally, termination. They do not wait forever. The healthy nodes eventually decide. Raft is one way to get those properties. It assumes crash stop failures, not Byzantine ones. So nodes might die or drop off the network, but they are not assumed to be lying, which is the whole thing with Byzantine fault tolerance. Before Raft, the algorithm everyone pointed at was Paxos, and Paxos is correct. Its safety has been proven, and that part is not really the main pain point of Paxos. The complaint about it is that it is hard to understand. You can read it fairly carefully and still walk away unsure about how the pieces fit together. It is also notoriously hard to build. Descriptions leave a lot of practical detail out, and those missing edge cases are usually where implementations go wrong. And finally, it is hard to teach. A team can feel like they know Paxos without actually sharing a clear picture of the protocol. So Raft's goal is the same guarantees, but designed so you can actually understand it. If you can explain why it works, you are in a much better position to implement it correctly. The algorithm does that by splitting consensus into three pieces. First is leader election. The cluster picks one node to coordinate writes. There is one leader per term and everyone else follows. Second is log replication. Clients send commands to the leader and the leader pushes log entries out to the followers. Data only moves in that one direction. And third is safety. Even when leaders crash in the middle of a write, you never apply two different commands at the same position in the log. We will come back to that after replication. Underneath all three is a strong leader. The leader decides where new entries go, and the followers do not negotiate a log among themselves. The leader pushes, and the followers never initiate writes. We are going to start with a few Raft primitives just to get some concepts straight, and then we will move on to those three subproblems. Raft does not sync the database itself and directly. It actually syncs a log, and each server runs the same state machine over that log. You apply those commands in order. First x is set to 1, then y is set to 7, and so on. And you do this on every machine that is following this log. And because we assume the machines are deterministic, the same log produces the same state on every single replica. So if every node has the same log in the same order, every node has the same state. The consensus problem in this picture is keeping those logs aligned. After that, you just run the commands in order. Now Raft divides time into terms. You can think of them as election cycles. Each term is just a number that counts upward, and in that sense, terms act as a logical clock. A term usually starts with an election, and if someone wins, you then get a stretch of normal operation under that leader. Sometimes the election actually fails and you get a split vote, or for example, nobody wins. And we will look back at this later, but basically at that term, there simply is no leader elected, and the numbers keep going and the cluster tries again. For the core algorithm, servers only talk to each other with two RPCs. The first is request vote, which is used during elections. A candidate is essentially asking, please vote for me in this term. The second is append entries, which is used to replicate log entries. The leader is sending commands and asking followers to append them to their logs. Now, there are also empty append entries that act as heartbeats. It is the same RPC just with no entries attached, meaning I am still here and I am the leader, so do not start an election. There is no separate heartbeat protocol, it is simply append entries with an empty list. Moving on to server states, every server is in one of the three states. It starts as a follower, and followers respond to RPCs, and they do not lead themselves. If a follower hears nothing for a while, no heartbeat, and it has no granted a vote, for example, it times out, becomes a candidate, and starts an election. If that election times out again by itself, it starts another one in a new term, and it tries again. If a candidate gets votes from a majority of the cluster, it becomes the leader. Finally, anyone can also fall back to a previous state. A candidate that discovers a current leader or a higher term becomes a follower again. A leader that sees a higher term steps down as well. Raft guarantees that there is at most one leader in a given term. Now, let's start with the leader election subproblem. We have a cluster of 5 nodes in our, let's say, distributed system. And if you lose 2, you still have a majority, right? They all come up as followers, let's say in term number 0, and there is no leader yet. Someone has to notice the silence and go first. Suppose they all use the same timeout and they all expire together at the same time, which would happen if they have the same timer. Everyone becomes a candidate and each one votes for itself and broadcasts request vote. So, there are 3 simple rules in Raft when it comes to voting. Rule number 1, first come, first served. You vote for the first valid candidate you hear. And rule number 2, at most 1 vote per term. And finally, rule number 3, reject a stale term, which means if someone is campaigning with an old term number, ignore them. Each candidate already spent its vote on itself in our example in the previous slide, and that's legal, but it is also a trap. Each node now has 1 out of 5 votes, and because all of them voted for themselves and sent request vote, and at the same time you can only vote for one server at a given term, there is a deadlock situation, as you can see. And if they even retry with the same timeout, do the re-election, this will go on forever. So you need a way to break the symmetry. And this is where the randomized timeouts concept in the Raft paper comes into play. Give every follower a random election timeout, for example in the range between 150 to 300 milliseconds. The bars are different lengths on purpose in the image. Let's say N2's timer hits 0 first. N2 becomes the only candidate. N2 asks the others for votes. Request votes goes out. 3 followers say yes. N2 already voted for itself, so that's 4 out of 5, and that is now the majority. N2 will become the leader for term number 1. Now, the leader, N2, has a job besides winning, and that is to stay the leader. It sends append entries, the empty versions, as heartbeats in a loop. Each one resets the follower's election timers, and so it prevents them from timing out. As long as those land in time, nobody starts a new race. And this is now a stable cluster. Writes can happen, and it can go on. But let's say the leader does actually fail. For example, N2 crashes. So what happens is that the heartbeats stop and the followers, eventually one of them will run out of timer and they will time out. So N2 is down and term 2 starts. Here, N4 and N5 have both timed out at the same time. Let's say in a worst case scenario, this can happen even with randomized timeouts. So you might get two candidates, and that is allowed again. It's just another election. In this case, we will have two possible scenarios. One of them grabs a majority, and you have a leader, and then you won't have a re-election, and the term will continue under normal operation. It is done. However, they can also split votes. This means we will have another round of elections, hoping this time a split vote won't happen. So that's leader election in Raft. Timeouts are random, so they don't usually expire together. Majority wins and the heartbeats hold the cluster. If the leader fails, followers time out and elect again. And as I said, at most one leader in a given term. Next on, we'll move to log replication, which is the second subproblem. A log entry has three fields. Term is 2, which is the term in which this entry was written, obviously. Index is 4, which is the position in the log. The first entry is index 1, the second is 2, and so on. And the command is set x equals 9, which is what the machine will run. One major property of Raft is called the log matching property, and it has two parts. If two logs have an entry with the same term and the same index, as you can see, they store the same command. A leader only writes one thing at a given index in a given term, and entries do not move around afterward. And the second part is if they agree on that pair, the logs are identical from the start of the log through that index, which means they have the same prefix essentially. That is why the consistency check on append entries can be so small. You check the previous index and the term, and you know the whole prefix matches. You can kind of prove this inductively if you think about it. Now, the normal flow, the client sits outside the cluster, obviously, and just to not get confused, a client is separate, right? It's not a follower, because followers, leaders, and candidates are all servers. The client is whoever wants to do something like set equals 9, for example, through an application. The client sends that command to the leader, and the leader appends it to its own log first. Term 2, set x equals 9. Followers do not propose this, the leader does. Then the leader pushes append entries to the followers and they write the same entry onto their own logs. So the leader appends first, then pushes, followers append, then acknowledge. They never initiate their write themselves. We have not committed these yet. Copies exist, but the cluster has not yet said that this entry is locked in, meaning it is safe to apply, which means it is safe to run in the machine. To elaborate what I mean exactly, let's look at this 3-node cluster. N1 is the leader, N1 and N2 already have the entry, and N3 is behind, let's say it crashed along the way and now it has recently restarted. That is fine, because we have 2 out of 3, which is the majority, having the same log entries, meaning the same term and the same index. For an entry from the leader's current term, this is term 2 and N1 is the term 2 leader, that majority is enough to commit. N3 can catch up later. A slow follower does not stall the cluster, does not hold it back. This counting rule is for entries created in this leader's term. Entries left over from an earlier term are a bit more careful, and we will cover that in safety. Once it is committed, servers apply it to the state machine in log order, and x becomes 9. Then the leader can answer the client. Committing means the log is safe to apply. Apply means the state machine actually ran it, and the client hears back after that apply. Now let's say N2 is the new leader. Its log has terms 1, 1, 3, 3. N3 still has an extra leftover from an old leader. At index 3, it has term 2, and with the command x equals 9, which is different as you can see. It is a different term but the same index. That is a real conflict, and the log matching property does not allow two different commands to sit there forever. The leader sends append entries with a previous log index. N3 does not have a matching previous entry, as we can see, so the check fails. The leader keeps a next index for each follower. On failure, it decrements next index for N3 and tries again. It walks backward until it finds the last point where the two logs agree. Then N3 truncates everything after that point and appends the leader's entries. The leader's log wins and the followers are brought into line. A leader never rewrites its own log, it only fixes followers. Let's put the pieces together. N1 was the leader. It replicated set x equals 42 to node number 2. That is a majority on a 3-node cluster in the current term. So this entry is committed. N3 never got up. That is a majority on a 3-node cluster in the current term, so this entry is committed. N3 never got it. Now, N1 crashes. Let's say N2 wins the election and becomes the leader. Notice that its log is up to date. That is not luck. A candidate with a stale log, like N3, cannot and should not be able to win, based on the voting rules and everything we went through in leader election. The new leader, N2, sends append entries, and N3 gets updated. The committed entry is still there. It was never lost. 4 things to take away in this part, and then we will move on to safety. First, push. The leader appends first, then replicates. Data only flows in that one direction. Second, majority. The current term entry on a majority is committed. The rest catch up later. You do not wait for every node. Third, conflict. If a follower disagrees, the current leader's log is authoritative. Fourth, crash. Once an entry is committed, it survives a leader death. The next leader already has it. So, with this we wrap up the log replication part and we will move on to safety. We have election and we have replication, but those two pieces are not quite enough on their own. They do not yet guarantee that every state machine runs exactly the same commands in the same order. Here is the kind of failure that is still possible. A follower can be unavailable while the leader commits several entries. Later on, that follower comes back, wins an election, and overwrites those entries with new ones. At that point, different machines would execute different sequences. Safety is what closes that gap. We restrict who is allowed to become leader, so a new leader already has everything that was committed in earlier terms, and then we make the commit rule a little more precise. Safety is what closes that gap. We restrict who is allowed to become leader, so a new leader already has everything that was committed in earlier terms, and then we make the commit rule a little more precise. The extra rule is this: you only grant a vote if the candidate's log is at least as up to date as yours, which we already covered earlier in the video. If the last terms are different, the log with the higher last term is more up to date. If those last terms are the same, then the longer log is more up to date, meaning the candidate's last index has to be at least as large as the voters. And here is why that is enough. A candidate needs a majority to win, and a committed entry already sits on a majority. Those two majorities have to overlap, so at least one voter already has the committed entry. That voter only says yes if the candidate is at least as up to date. Here the situation is different. N1 is now the current leader in the term 4. But x equals 9 is an old entry from term 2. Even though x equals 9 is on N1 and N2, which is a majority, it is not from the leader's current term. That's the important thing here, current term. So N1 cannot commit it just by counting those copies. Why not? N3 has a different command, y equals 1, from term 3 at the same index. Because term 3 is newer than term 2, N3's log is considered more up to date, right? So let's say N1 crashes now. N3 can still win an election and overwrite x equals 9 with y equals 1 on N2. So if we had already called x equals 9 committed, two machines could eventually apply different commands at the same index. That is why a majority of copies is not enough for an older entry, only for the current entry. N1 cannot safely commit that older entry until it replicates a new term 4 entry, c equals 1, let's say, onto a majority. That entry is from N1's current term, so it can be committed directly. Once it commits, all earlier entries in the same log, including x equals 9, become committed as well. N3 can no longer win because its log now ends in term 3. Just to quickly connect this back to the earlier commit rule part in log replication, there the entry was from the leader's current term, as I said. So majority was enough there. Here it is an older entry from term 2. So in a nutshell, the leader appends a current term entry, replicates it to a majority of followers, and commits it after that, and also, every entry before it. So let's put those two ideas together and you get leader completeness. In term 1, N1 commits x equals 5. Later, N2 is leader in term 2, and the same committed entry is already in its log. And then N3 leads in term 3, and it still has it. Once an entry is committed, every future leader has that entry. The Raft paper that was first published names 5 properties that are supposed to hold at all times. We already have met all of them along the way, so this is just a recap of how they fit together. Election safety, which basically means at most one leader in a given term. Leader append only. This is another property which basically means a leader only adds to its own entries. It never writes or deletes anything. And we already saw this in conflict resolution, for example. Log matching. If two logs share the same term and the same index, then they match from the start of the log through that index. Leader completeness, which means if an entry is committed in term T, every later leader has that as well. This was just a practical summary. The paper goes much further in the safety guarantee section and gives the detailed safety arguments and even the proofs, showing exactly why these properties hold. Raft is widely used in production. etcd uses it to manage Kubernetes clusters, and also CockroachDB uses it, for example, and there are many more systems built on the same ideas. So that's the Raft essentials: leader election, log replication, and safety, put together in a way that is practical to understand and implement. In the future, I will go more in depth about Raft.